What specific problem does the proposed reasoning reward models, REASRMS, aim to solve in the context of generalist reward modeling, and why is this important for LLM applications?
The proposed reasoning reward models, REASRMS, aim to address the limitations of existing reward models in generalist reward modeling, particularly the challenges posed by diverse and complex evaluation criteria across various domains. Traditional scalar-based reward models lack transparency and reasoning capabilities, while generative reward models often provide superficial reasoning that is insufficient for nuanced judgment. By framing reward modeling as a reasoning task, REASRMS enhances interpretability and accuracy through structured reasoning chains, which significantly improve performance on reasoning-intensive tasks. This advancement is crucial for large language model (LLM) applications, as it enables more robust and versatile performance across a wide range of tasks, ultimately leading to better decision-making and user interactions. The integration of reasoning capabilities ensures that the models can handle complex evaluations effectively, which is essential for the broader applicability of LLMs in real-world scenarios.
How does the proposed method RM-R1 work? Illustrate the step-by-step process from model initialization to deployment, focusing on the roles of reasoning, trace distillation, and reinforcement learning, RL.
The proposed method RM-R1 begins with the initialization of an off-the-shelf instruction-tuned model, such as QWEN2, 5-14b instruct. The first step involves synthesizing high-quality reasoning traces by querying an oracle model to generate structured justifications for selected answers, which are then used to create a distillation dataset. This dataset is utilized to fine-tune the model, enhancing its reasoning capabilities before it undergoes reinforcement learning (RL) training. During the RL phase, RM-R1 is treated as a policy model, optimizing its performance based on a reward function that emphasizes correctness and leverages the reasoning traces generated in the distillation stage. Finally, RM-R1 is deployed, demonstrating improved interpretability and accuracy in various tasks, as it effectively integrates structured reasoning into its evaluation process.
Can you provide a simple yet illustrative example that showcases how RM-R1 makes a decision in a preference judgment scenario? Walk through the main algorithm steps using this example.
In a preference judgment scenario, RM-R1 first classifies the input task into either a chat or reasoning type. For instance, if the task involves evaluating 2 chatbot responses to a medical question, RM-R1 identifies it as a reasoning task. Next, RM-R1 generates a structured reasoning trace by solving the problem itself, which includes identifying the correct answer and justifying it based on accuracy and relevance. After constructing this reasoning trace, RM-R1 compares the 2 responses, applying the evaluation rubrics it generated earlier, such as correctness and logical coherence. Finally, RM-R1 selects the preferred response based on its comprehensive evaluation, ensuring that the decision is grounded in the content and adheres to the established rubrics, leading to a coherent and interpretable judgment process.
What are the theoretical or practical benefits of using RM-R1 compared to traditional scalar-based and generative-based reward models?
The RM-R1 model offers significant theoretical and practical advantages over traditional scalar-based and generative-based reward models. Theoretically, RM-R1 enhances interpretability and accuracy by framing reward modeling as a reasoning process, which allows for coherent and structured reasoning traces that mirror human evaluative processes. Practically, RM-R1 consistently outperforms scalar-based models, which lack transparency and often focus on superficial features, and generative models, which may provide superficial reasoning. Empirical results show that RM-R1 achieves state-of-the-art performance across various benchmarks, outperforming larger models by up to 13.8% in accuracy, demonstrating its effectiveness in reasoning-heavy tasks. Additionally, RM-R1's training pipeline, which includes structured reasoning distillation and reinforcement learning, enables it to generalize well across diverse domains, making it a versatile tool for a wide range of applications.
How has RM-R1 been validated or tested? Describe the experimental design, datasets used, and key performance metrics that demonstrate its effectiveness.
RM-R1 has been validated through extensive empirical analyses across 3 key benchmarks: Reward Bench, RM Bench, and RMB, which evaluate its performance in various domains such as chat, reasoning, and safety. The experimental design involved comparing RM-R1 against both scalar and generative reward models, including models like GPT-4o and DeepSeek GRM, to assess its accuracy and interpretability. Key performance metrics included accuracy improvements, where RM-R1 outperformed larger models by up to 13.8% on these benchmarks, demonstrating its superior reasoning capabilities. Additionally, RM-R1 was trained on a high-quality collection of pairwise preference data, ensuring robust evaluation across diverse tasks. The results indicated that RM-R1 consistently achieved state-of-the-art performance, validating the effectiveness of its reasoning-based training approach.
What limitations or potential drawbacks did the authors identify in their approach, particularly regarding generalizability or reliance on specific datasets?
The authors identified several limitations in their approach, particularly concerning generalizability and reliance on specific datasets. They noted that distilled models, while effective, often suffer from overfitting to certain patterns in the distillation data, which can limit their ability to generalize across diverse tasks. Additionally, they highlighted a significant issue with the Skywork dataset, where a strong spurious correlation was observed, leading to biased training outcomes. Specifically, responses from the Magpie_Ultra source exhibited systematic biases that could adversely affect model performance. The authors also acknowledged that while their reasoning reward models, REASRMS, demonstrated strong performance across various domains, the reliance on curated datasets for training could still pose challenges in achieving robust generalization in real-world applications. Overall, these factors underscore the need for careful dataset selection and model training strategies to enhance the generalizability of their models.